Okay, so unlike yesterday's talk, this is supposed to be a research talk. So I won't go through a lot of mathematical details, which I barely tried to do yesterday. Okay. So here I guess you know the second part of the title, complex networks. By now you are probably bombarded with what is complex networks and so on. So I'll start with what is extreme event. Here are some examples. Actually this I picked up when there were heavy rains in Chennai some years back in 2015. One of the heaviest rains in recent memory, I think. So this is, as you can see, between 1st of October and 31st of December. This is the average kind of daily rainfall in Chennai. So you see that somewhere between 10th of November and maybe around 25th of November, there are these large heavy days of rainfall. Okay. This red line here represents the average. Okay. So you can think of it as a long-term average, and these are the large excursions away from the average. So whenever you see things like this, you would say that this is an extreme event. So anything which is far away from the norm, far away from what you expect, would be an extreme event. And this is the state of Chennai airport on that day or around that day, okay, filled with water. So clearly tells you that extreme event also means that there is a huge amount of damage to be expected to property, to people and so on. So it's worth studying extreme events in general. And there are all other kinds of extreme events which you might not even recognize as extreme events. So cyclones, rainfall, drought, everyone would immediately recognize as an extreme event. But something like a busy web server, traffic is so common that we won't even recognize it as away from the average. Even when I was coming from home just now, we were stuck at several places. So busy web server, for instance, if you keep, sometimes there are some heavy duty web servers which go down simply because there are too many requests to that web server. It's not able to service the requests and it goes down. Like for instance, you try and book a Tatkal ticket, everything finishes in the first 1 minute when it starts, because there are just far too many people trying to attempt to do that. So those are kind of unseen examples of extreme events. So here again some more pictures of what extreme event can be. So this is the ground displacement during an earthquake. So this is until when it was peaceful, and then begins the real earthquake and you see large amplitude oscillations. That's another example of extreme event. Okay, this is a stock market which has fallen quite a bit in a very short time. In fact, this is 10 a.m. and 3 p.m. So, but recovered very quickly. So these are examples of extreme events. So what would an extreme event be? To frame it as a mathematical question. So you think of having a time series like this. This x could be any variable that you want to think of, temperature, number of vehicles, whatever, as a function of possibly time. It can even be parameter, but here the parameter is time itself. And you set a threshold. You say that anything above that is somehow an extreme event for me. And so this points which are marked in blue, they are the extreme events. Okay. So extreme event is something where the value of your time series is larger than the threshold that you have identified. You can relate it to, for instance, the capacity of the system to service the flux. Maybe you will understand what it means in a while. So you can convert this time series into a distribution like this, f of x. Okay, so if you had a long recording of this time series, convert it into a probability distribution, and when you do that, the events which are marked in blue here will essentially fall in the tail of the distribution here. Okay, so which means that you are actually looking at events which occur very rarely, but nevertheless of sufficient serious importance that you need to pay attention to it.
I think Anindya discussed this thing where he said that that's the price time series, this is the return distribution.
Yeah, so yeah, that is, yeah, right. So the question, or at least one straightforward question, you want to start with this. What can we say about the properties of events which fall in the tail of the distribution? So here the setting is not a network, simply one time series. It could be time series of anything that you like. So there are study of extreme events is quite old. There is the classical extreme value theory, which is at least 100 years old, essentially for uncorrelated processes, meaning that the processes doesn't have any memory. In such cases, it tells you that if you take the block extreme values, then they finally tend to one of the three possible distributions. I don't have a slide for that, but maybe you heard of things like Weibull distribution or a Frechet distribution and so on. They are part of those classical extreme value theory. It doesn't matter from where your time series comes from, which process generates it. It's independent of the physical process that generates it. All that matters is you need to take block maxima, and it should be an uncorrelated process. And another question of importance is return intervals. So for instance, if you look at this, an event has occurred at this point, when will it occur again? So this time between two occurrence of an extreme event is called a return interval. Time interval between occurrence of successive extreme events. So the question is, what is the distribution of that return intervals? That is a stochastic quantity. And for uncorrelated processes, I will show you that it is a simple exponential distribution, but for correlated process, it is an outstanding problem, not easy to solve. And of course, you also would like to know what is the probability of occurrence. So you would like to know what is the probability of occurrence of this event. Maybe you would even like to predict when is it likely to occur. Is it going to be a heavy rain in Chennai today and things like that. And there are many other interesting questions, but at least these ones are the major ones. At least for the first part of this talk, which does not involve any network, we shall, yeah.
Can't you put some lower threshold below which you can?
Yeah, you can do that. You can equivalently also have a lower threshold and look for the distribution of the minima. Yeah, that's also possible. But in many real cases, that is more like a yeah, that's also of interest, like saying what is the lowest temperature that was there in some place and so on. It's more like a trivia rather than something that causes major damage. It can be of interest in some cases.
But in the market, actually.
Yeah, the lower one matters. Yeah, like it depends. In some cases, the larger one matters. Some cases, the lower one matters. Yeah. So for this part, we shall differentiate between an uncorrelated process and a correlated process. So just to tell you what an uncorrelated process would be, it would mean that we have a correlation function. Which would, suppose I have, this is my time series x of t. So you have x of t plus tau, average over it. So this will be your C of tau. And if something has a fast decay of correlations, either it is decaying exponentially, that is one possibility, or it can almost be memoryless, where it basically is like a delta function. So this is your 0, it loses memory immediately. Okay. So those are convenient cases. So if you are to model something, if the situation is that it has a very short term memory or no memory, that is best. Makes life easier because the system does not remember where it began from after a long time. So you don't need to worry about where it started, how it started. It's just enough to know where it is now to tell something about the next step. Okay. So that is.
Set the threshold.
Huh?
How does one set the threshold?
No, this one does not require setting a threshold. Just take the time series as it is. Just do this. That's all. So this is not for extreme event, just for the entire time series.
In order to classify it as an extreme event, you have to.
Oh, that is by, okay, so there are many ways. One is of course by trial and error, or you can compute, for example, the standard deviation and say that extreme event is more than certain number of standard deviations away, if you want to be very objective about it.
You can't define for arbitrary, like t in the.
Yeah, so this is as a function of tau there.
So we can take any t in the time series. Data.
Yeah, you can take any time series and do this. This is a simple averaging process.
So when you actually want to see the probability of some event, some extreme event occurring at time t, you would necessarily have to know some general information about the return interval distribution.
No, you will never start by saying, okay, you can start by saying that you assume some probability about occurrence of an event, but then using that you should be able to calculate the return interval distribution. You should go through some process to calculate that. This is just an autocorrelation function. This simply tells you whether the system you are working with has any memory or it has no memory at all. So these are examples where either the memory is short or almost no memory, as opposed to the other case where it can have a power law decay, which means that the decay is really very slow. This is 0 here, so which means that it remembers its long past even from the time it started the first value. Okay, and those are often difficult things to work with, because to model the present value of the series, you need to know the past values for a considerably long time. Okay, and you need to maybe write some equations and model that. Yeah. Why is that? This one. This one. Yeah, I will come to that. So this is a short memory process. A long memory process has a power law decay, like I have tried to draw there. And this has a power law like tau to the power gamma, where gamma lies between 0 and 1. So when gamma lies between 0 and 1, you can do that yourself. Typical scales in the system actually diverges. There is no typical time scale, only when gamma lies between 0 and 1. So for instance, the second moment of this distribution will diverge, which means that it lacks a typical time scale. Whereas for an exponential distribution, you can actually calculate the typical time scale. Okay. Mean and second moment are the same for the exponential case. So systems such as that don't have a typical time scale associated with that. But if you go with gamma greater than 1, they will have a typical time scale. So this is in some sense the worst case scenario, a modeler's nightmare, so to speak. So for example, here is a finance data from Standard and Poor Index. Okay. So the autocorrelation function as a function of this time lag shows it's a straight line here, at least in this region, when plotted in log-log plot. Okay. So that is a signature that it has a power law tail. So a lot of natural processes, fortunately and unfortunately, fall in this class, where they have slow decay of correlations, which means they have very long memory. It's fortunate because then you have to break your head how to work with it, how to model it. Unfortunate because it makes modeling difficult. So pretty much any man-made or natural process that you take will show something like this. So here are many other examples. This is for solar flares. So all these y-axis are somehow related to the autocorrelation function, and you can see a reasonable power law in most of them. Actually, these are okay. These are not the okay. So so if you get the idea of long and short memory processes, there are whole lots of processes which are which show long memory. And the quantity of interest is the return time distribution, the time interval distribution of the time interval between successive occurrence of extreme event. So what is plotted here is such a distribution, the distribution between successive occurrences of extreme event. So in this case it is solar flare, the time time interval between two occurrences of a solar flare. This is the inter-occurrence time for extreme events taken from different earthquake catalogs and so on. So, this one, all these are essentially stretched exponential distributions. For instance, this line that you see here is a stretched exponential distribution, and so is this continuous line that you see here. And in fact, many other things you can think of as an extreme event. So, if you take a large text, you can ask for where does a particular word appear. So, the number of words between successive appearance of a word you can think of as the interval between extreme events. So, you can do a similar calculation, and there again it turns out that the time interval between such occurrences is a stretched exponential distribution. And stretched yeah.
When you say it's hard to model, it's because of the availability of data of long-term steps.
No, it is simply because you need to take into account where it started from. It's much more difficult. So, stretched exponential distribution, for those who have not met it, is basically a product of a exponential term like this. So, you can see e power, this alpha is a constant, what matters is e power minus tau to the power beta, and then there is a tau power beta minus 1. So, there is a power law like term multiplied to a exponential like term. Okay. So, this kind of stretches the usual exponential. And so, more than around 15 years back or so, we kind of.
So the beta is in the power.
Yeah, so there is a beta here as well as here, yes.
So that the second beta is in the power of.
Correct. So, we tried to work with this with these results. At that time, most of it was either a fitting or simply a guess based on the data itself, like data like these things. So, we actually tried to model it, and okay, I am going to skip all the derivation here and just show the final result, which actually tells you that for stationary long range correlated time series under certain approximation. So, the correlated time series has this correlation exponent gamma, where gamma lies between 0 and 1. So, that is like the worst case scenario, as I said, and in that case the return interval distribution basically turns out to be this. Okay. Now, you can once again identify that there is a power law apart from this constant that you see here, there is a power law term here, r to the power 1 minus gamma, where gamma is simply this autocorrelation exponent, and again there is a e power some constant sitting here and r power gamma. Okay. And so, this is one of the few analytical results that deal with this question. And the interesting features are when you put gamma equal to 1, actually you should get to the uncorrelated limit, and it does give you the correct uncorrelated limit, meaning that the return interval distribution just becomes exponential, which is the correct limit. And for very small values of r, power law dominates, and which also agrees with the empirical data, and for large r, meaning large intervals, stretched exponential term dominates. So, all that comes out of this, and so here is one sort of confirmation of that with the measured wind data, where the autocorrelation exponent is about 0.24. So, it lies between 0 and 1, and this is the theoretical result that I just showed in reasonably good agreement with the data. Thanks. Okay. Okay. So, now so this is something that we did almost 15 years ago for a single time series that has long range correlation, or in other words that has long memory. Now, after that I started thinking about can we look at extreme events on networks, So here is some kind of motivation as to what an extreme event on a network, how will it, how different it will be compared to maybe a extreme event on a univariate time series. So you see this headline which is taken from Pune Times of India. So it shows that traffic snarl which started at some place had a cascading effect. Now that is something that is common on networks. So something that happens in one place just doesn't stay there. An extreme event in one place has a cascading effect. Okay. And in this case it is a traffic that has cascaded across the city and led to many more traffic snarls across the city. So this is sometime in 2012, August 14. It's no, actually the date is August 14, 2008. Okay. And not that it has become better now. You can't avoid it. It will keep happening. What
is going below that station? Like extreme event means you see the time series of.
Yeah, that's right. I will show I'll define what an extreme event here in a network scenario. Okay, but it's the same sense. There's no difference. You don't have a different idea of extreme event. And another thing which maybe some of you might have experienced is this happened in 2012 when for 2 successive days, July 31st and August 1st in 2012, there was a blackout. Much of North India was affected by the blackout. 2 successive days, almost 600 million people were left without power. So this is Delhi Metro saying that there's power failure and no trains. So anyway, so again, if you look at situations like this also is because of cascading effect. So what started as, let's say, a malfunctioning transformer in one place, because you kind of networked the entire power grid system, one transformer does not work, so the load of that actually is now shared by the others to which it is connected. So they are not able to anymore take that load, they go down, and so on. It cascades very soon, and large regions of the country basically are left without power. Okay. So this is one kind of phenomena that can occur in a networked situation. Okay. So now once again it's the same slide that I showed you before. So extreme event is same thing. So the only question to ask is what happens to extreme events on complex networks. Okay. So here I will try and illustrate this with the networked scenario. So here you not only need a network, but you also need something on the network which will tell you what the event is. So here we use the model of random walks on complex networks. So which means that there are large number of walkers. You have a large network, many nodes and many edges, and a large number of walkers are there on the network. Each of the walker is independently doing a random walk on the network. I suppose all of you know what random walk is, right? Okay. Essentially just choose your next point randomly by tossing a coin. Okay. So you don't have a specific goal to go anywhere in particular. And so here the events are simply the random walkers. So something like this here could mean that this kind of a graph in that setting would simply mean that I am looking at a particular node, maybe some node like this, and I am just measuring the number of walkers at that node at every instant of time. And because walkers are randomly walking across the network, sometimes there will be more walkers, sometimes there will be less walkers. Purely by chance, suddenly there will be a large number of walkers at the same time. So for example, you look at this snapshot at some particular time, say t equal to 0, these are the 1, 2, 5 walkers, the blue ones in a small snapshot of the network. But at some other time, suddenly there are 4 of them sitting on the same node. So this possibly could be an extreme event for you. Okay. So extreme event in this kind of scenario is based on number of walkers in a given node on the network. So this might look like a very unreal situation because no one does a general random walk in any street, but nevertheless these are useful templates to think about many flows on network, many kinds of flux that is going on network. So, it could be like packets of information, the IP packets passing through the network, or maybe even vehicles on highways and so on. So, here the extreme events happen because there are natural fluctuations in the walkers passing through the a particular node. Okay. So, you are not inducing anything, it is not like some low pressure area is inducing a cyclone in Chennai and things like that. Okay. So, you can't, it is simply an inherent fluctuation in the system because it is a stochastic process. It is inherently inducing certain fluctuation, and suddenly at some points that fluctuation becomes large enough that you call it an extreme event. So, this is the setting. I have extreme events on the nodes of the network. So, I am going to consider a connected but undirected network, and n nodes, and there are total of k edges and total of w non-interacting walkers. So, each walker does its own thing, they do not talk among each other and decide the path. And in such case, suppose you focus yourself on one particular node, let us say ith node of the network, you can ask what is the distribution of the walkers passing through that node, and that is actually a binomial distribution. So, I have removed many of the mathematical equations here, but that will be a binomial distribution. And so, if you are focused on the same node and ask a question, are there any extreme events in that node, then you would define your threshold somewhere, okay, and say that all the walkers, when there are large number of walkers like this, those will be my extreme events. So, the extreme events happen when W is large, which means large number of walkers are somehow quite by chance coming together at a particular node. They will disperse off immediately at the next moment. Okay. So, I have chosen some threshold tau. Okay. Now, how do I choose this threshold? So, this setting, this problem is exactly solvable. Okay. You can solve it analytically completely. And how do you choose the threshold? You can put a constant threshold and say that anything above that is an extreme event. The one problem will be that some nodes will not attract many walkers. So, they will never ever have an extreme event if you set your threshold very high, or if you set your threshold very low, every node will show extreme event all the time. So, that is very unnatural. That is like, I do not know how many of you recognize this picture from R.K. Narayan's fictional town Malgudi. This is the statue of Sir Lally. So, in this town Malgudi, I think even when there are, if you read all of R.K. Narayan's works, you will realize that even when 4 or 5 cars come, it is an extreme event because it becomes the talk of the town. Whereas not in a place like this Anna flyover here in Chennai, where thousands of vehicles pass every minute, that 4 cars or 10 cars does not make any difference at all. So, what is extreme in one situation is not extreme in another. So, to have an extreme event in a place like this Anna flyover, you need to set your threshold very high, whereas here even a threshold of 1 car becomes an extreme event. So, you set the threshold based on variance in each node or based on the typical flux that is passing through in that node. So, it is the mean flux plus some number that you choose times the standard deviation. Okay. So, you can say more than mean plus the 4 standard deviation is my sense of extreme event. And in this, for this problem where you are working with random walkers, you can calculate all this analytically, and everything depends only on the k, which is the degree of ith node. So, I here stands for ith node, index of the node. So, the threshold simply depends only on the degree.
What is capital?
What is cap W?
Capital K.
Capital K is the total number of edges. Yeah, total edges.
Here it's similar to the Laplacian times the.
Yeah, so this actually the governing equations are, we can start from Laplacian that I wrote down. Okay, so this is my threshold for extremes. It's proportional to the mean flux, and you can actually calculate the probability for the occurrence of extreme events. So you need to essentially write down this distribution and integrate over these values. That's what you need to do. Okay, so I'm again skipping those things, but if you do all that, you can finally write an expression in terms of some special functions. Okay. But you can show that it's essentially like a power law in the degree of ith node. So the point is that it depends only on the degree of the node in question. Just one second. And okay, yeah. So q is a number that you can choose. So you can, if you put 2, you are saying that more than 2 sigma events are extreme events. If you put 4, it means more than 4 sigma events are extreme events. Okay, to understand this large statement, let's plot this and see. So if you plot this, you will, so let's look at this, the top figure alone. What you see is the probability for the occurrence of extreme events on the y axis as a function of the degree of node. So this is for a large scale free network, and there could be many nodes with the same degree. For instance, there could be many nodes that have degree 9, for instance. So what you do is you simply average over all the degrees that have degree 9 or degree 81 or whatever, okay, and it's plotted in log plot. So the thing that you notice is that these are the small degree parts, and these are the hubs of the network. Quite ironically, the hubs on the network, they have a small probability for the occurrence of extreme events. This number is small on an average compared to this part where the probability for occurrence of extreme events is larger.
So by extreme events, you mean a lot of workers,
Lot of random walkers, yeah, that's right.
What is I there?
Okay, so I is a beta function. So it's one of those special functions of mathematical physics. Yeah, it's actually an incomplete beta function. Yeah. Okay, so that is something somewhat not quite something that you could have guessed immediately, because hubs would mean that a node which has a large number of edges, and so typically it attracts large number of walkers to itself because there are more pathways for walkers to come in. Whereas a node which has a fewer degree, the degree is small, it has just maybe 1 or 2 edges. So the number of pathways by which walkers can come in and go out is also small, is fewer, so that is also small. But nevertheless, when you take into account the typical flux passing through all these, which means that you are putting them on a same scale, same footing, you are treating them, all of them, on a same footing. When you do that, it turns out that somehow the small degree nodes have higher probability on an average compared to the large degree nodes. Yeah. I'll tell you. Okay, so here you can even ignore the delta. This is for exactly the problem that I described. So in the problem that I described, I said there are total of W non-interacting walkers. So the total number of walkers does not change in the network. There are no new walkers born in the network, or they don't die and so on. So W remains W. But on the other hand, you can say that somehow this result is special because you taken W to be a constant. You can relax that requirement. You can say that I will allow W to be a random variable. Total number of walkers will not be a constant on the network. So there will be, at every time step, some might leave the network, some will enter the network. So even in such cases where the delta, which represents that variability in the walkers, is not 0, even then basically same formula holds. Actually there is a different formula, but more or less it gives you the same kind of result. This is not empirical data. So this blue dots that you see is by simulating the random walk on the network. Yeah. So what is compared here is the analytical result, which is this functional form, and this is directly you simulate, put the this many number of random walkers. Okay, the numbers are not given. I thought somewhere that numbers was given. Okay, so you actually put in the random walkers and do the simulations and calculate the probabilities and plot these data points. Okay, so this is what we saw, random walk on networks. What I call as conservative model is when the total number of walkers is a constant. Yeah.
Did the analysis consider any specific topology of the network?
So these this result actually does not depend on the topology of the network. You can put in any topology, but this particular feature will come only when you have a large variability in your degree. So which means that this thing won't show up very nicely in a Erdos-Renyi network. So there scale-free network was used for this particular simulation. And okay, so yeah.
What if we vary the number of walkers also, because
That is what I have done. So this is variation of number of walkers. Yeah.
So will the result be different if it's a directed network?
So the functional form is slightly different. You can take into account that capital W is not a constant, total number of walkers. The result is slightly different, but as you can see, this feature is the same, that the higher probability in this region versus low probability here. That doesn't change. Okay, so this is what I just described. The walking rule or the algorithm by which you move the flux around is the random walk. But actually you can make it a lot more complicated, take it more closer to reality in some sense by saying that I am going to at every point in the node I am going to add a buffer, okay, which will so basically that's the amount of capacity that the node will have. So if a large number of walkers suddenly come in here and it exceeds the buffer, then this this node will not be able to take that walker. It's like saying that you have a, let's say, a junction, the closest junction here, and already it is clogged with cars. Can I now bring some more cars and put in there? You cannot, okay, because that junction has some capacity to it. No, they'll have to go back. So there is a rejection probability in the sense that when a walker, if it is already full and the walker tries to go from here to here, it will be rejected by this node, which means it has to go back here. So which means that you actually put in many other such rules, not just the standard random walk. It's the random walk plus put in additional rules. Additional rules for absorption, meaning that if the walker let's say has in some sense reached the destination, it will get absorbed at that node. And there is also a birth probability. So you can start with the clean slate. You start with the with no walkers on the network, and every node has a rate at which it will give rise to walkers. So this is a different model where you don't need to initially put in W walkers, just start with 0 walkers and the nodes will give rise to walkers. And they will keep moving, there might be, they might exceed the capacity of this buffer, in which case they cannot go there. All these will happen in such a situation. Yeah, there is also absorption rate. So it's kind of more complicated than the former model. So again, I'm not going to discuss this result in very great detail, except to point out that what you will see, there will be two different kinds of general phenomena that you will see. One, you will have a free flow state like this, which means that nowhere the, more or less, nowhere the capacities are exceeded. So generally there is a free flow of walkers everywhere. No one is getting like kind of held up in one place. On the other hand, for some other parameter choices, see, each one of them is a parameter. All this birth probability, absorption probability, rejection probability, you can think of them in terms of rates. All of them are parameters, and for certain other parameters, it's possible that the total number of walkers is increasing. Maybe if you put in a large birth probability, it's going to throw up, keep creating more and more walkers and clog the network. So, in such cases you will get a total number of walkers as a function of time will keep increasing on the network, so much so that you will finally come to a state where nothing is able to move, everywhere the buffers are full. So, that is a congested state. So, in general what you will see is a transition. So, you can plot it as a function of many parameters, but here it is shown as a function of the birth rate at average birth rate, which is assumed same across all the nodes. And so, you can see that there is this transition from a free flow state to a jamming state. Okay. So, here life is different, it is not as simple as the previous model. So, extreme event properties in free flow state can be still, you can think about extreme events in the free flow state because more or less it is like a stationary time series. You can ask, is there some way it is exceeding the, you get large fluctuations here. Even in a free flow state occasionally you can have large fluctuation. But in a congested state nothing moves. So, essentially things get bad enough that there is no movement at all. And even here when you are in the free flow state still the same result, the earlier result holds good, that small degree nodes will have more probability of extreme events. Okay. So, beta I think is this rejection probability. So, when you when a walker jumps from one node to another node, if that buffer is already full it will reject it. So, it has to come back to where it started from. Yeah.
Is there any study for the variation where it might not be a random walk, it's a strategic movement?
Yeah, there are many such studies. Even we have done one such study. So, you need to define your rule, what you want to do. So, for instance, if you want to study real traffic, you need to really implement a traffic model on the network, which will be more complicated than this. The nice thing about this is that it captures some aspects of reality, but you can solve it analytically, mathematically.
If the walker solves the buffer, if the walker, so will it return back or like go somewhere?
No, it has to return back to where it started.
Why?
Well, that is a rule. Anyway, these are rules that you create. You can create different rules if you want.
So technically, if you can imagine it.
See, you can go to a different point, but go back to where you started and then go to a different point.
But actually, you won't actually be going to the point.
Yeah.
Right? You just
Yeah. See, the way you implement is you decide beforehand whether it can. It means that you will be forced to stay back. Suppose it's in a situation where wherever it can go is all the this one is full, the buffer is full. Then it can't move at all anywhere. So it's stuck in that place. So there are many such rules which are implemented in practice but not written here. Okay. Okay. So now I'll change gears. Now till now I have been thinking my sense of extreme event is extreme event on the node of a network, but you can also think of extreme event on the edges. Okay. I mean, at first sight it might even appear that you can just exchange node to be a edge and edge to be a node and same results will hold good. That is not true. It does not work like that. So, for instance, if there is a walker here at time t minus 1 and this walker actually goes to, let us say, this node j at time t, then basically the walker essentially passes through this edge which is labeled as ij. Okay. So, that is the setting here. So, if there are many walkers on the network, there will be many walkers who may be going from here to there or here to here. So, you add all the walkers, that will be the traffic on this edge. So, here is it. So, for instance, let us say at some particular time t minus 1, there is a ni walkers here and nj walkers here. Not all of those, and my interest is to find how many walkers are there in this edge that connects I and j. So, if there are ni walkers here, not all of them will actually take this edge and go here, only some of them will go because others may try to take this edge and go elsewhere. Okay. So, it can so happen that of these Ni, only Li of them want to take this edge and go here, and similarly from this Nj, only some of them, which is Lj, will take this node and go here. So which means that there is Li going from here to here and Lj going from here to here. So now you can define two different quantities. One is what you call as the load. Load is simply the total number of walkers in that edge, which is simply Li plus Lj. Flux is the net number of walkers. You take into account somehow the direction, so it is Li minus Lj. So now this is your quantity of interest, load on the edge. Is there an extreme event in terms of load on the edge? Turns out that this is also an exactly solvable problem. You can calculate many things exactly, and it turns out that the probability of a load is again a binomial function, but only does not even depend on the node, it only depends on the larger parameters of the network. You take any network, it only depends on the total number of edges in the network and total number of walkers on the network. And so in this case, again you can work out everything exactly. The result again comes in terms of some complicated beta functions. So the probability for occurrence of extreme event turns out to be a constant independent of the edge that you are looking at. Whether the edge connects a hub and a hub, or a edge connects a hub and a small degree node, all that does not matter. In any of those cases, it is actually a constant. So this Q represents your sense of extreme event, the same Q that I had earlier on. Okay. So these green, blue and red colors are the simulation results, and these straight lines that you see here, flat straight lines, they are the analytical results. Then you can ask questions about is there any correlation between the extreme event. So we have already seen that extreme event can happen on a node, and there can also be an extreme event on the edge that connects this node to maybe some other node. So now you ask the question, if an extreme event happens in this node, does it imply that there will be an extreme event on the nodes, on the edges that originate from this node? No, it does not depend on the edge. It does not depend on the edge number, yeah. So here it is not the node that matters, it is the edge, yeah. Yeah.
So if there is an extreme event on the node, then on the edge, what can that say about this?
Yeah, that is right. So the question is, you are asking whether, let us say at a particular time, there was let us say at time t, there was an extreme event here. See, the walkers here now will have to disperse. So will they create an extreme event in one of the edges in the next time step? That is a question. Yeah.
So is there any intuitive reason why the probability of load does not depend on the nodes?
Okay, so that is simply because of this detailed balance. The reason that, suppose let us say if it actually depends, it will lead to like accumulation of particles in one particular node, which is not allowed in these models. Yeah, that is right, yeah. Particular to this class of models where detailed balance is respected.
And what if the edges have weights? How would this change in practice?
No, then it will depend on the edges, yeah. So here all the edges are assumed to have the same weight.
And
Basically,
and
and
edge
weight.
count.
Yeah, that's right, edge count. Okay, let me be very quick here. So the question is, are there correlations between extreme events on nodes and edges? Okay, I will just tell you what the result is without even trying to describe this graph. So there are the correlations are very, very minimal in the sense that there are correlations, but it's measurable, but it's very small. Okay. So for example, in about 10% of the cases, the extreme events in nodes are followed or preceded by extreme events on the edges. So if an extreme event acts on the happens on a node, only in 10% of the cases it translates into extreme event in the corresponding edges at the next time step. So, the effect is gets weaker as the degree of the nodes get larger, simply because an extreme event on a node gets scattered into many different edges, that it will not create a extreme on the edges if the degree is large. So, you can see the larger figure here. So, you do a lag 1 cross correlation, meaning correlate extreme event on the node with the extreme event on the edge at the next time step, that is lag 1. And this is across all the degrees of the network, and you see that only for small degrees there is some amount of correlation, where even the largest number that you see here is only 0.045. So, this scale can only go from 0 to 1, which means in that scale this is a very small number. Anyway, so the central lesson is that extreme events and in nodes and edges are very different kinds of extreme phenomena, and on networks with random walkers, an event in a node does not imply there will be an extreme event in the edge or vice versa. Okay, maybe I will just take a little more than 5 minutes to say something about one application that we did of all these things, not really extreme events, but so this is the work that we did around the COVID time. So here maybe let me directly go to so everyone who had lived in the last few years know that COVID somehow kind of marked our phases into before and after COVID, and you would also know that COVID spread because people came in contact with each other, and when people travel more they come in contact with each other more, so the infection spreads. So the basic premise is that in fact the basic premise is that however severe the infectious disease may be, it does not matter. The spread itself is caused by the mobility of people. So you may have the worst kind of the infectious disease, but if you are confined to a room here, it is not going to go out. But if you start moving around, you are spreading it around. In fact, this was noted in fact in 1918, Bombay had one of the worst of such plagues, and the Sanitary Commission of the Government of India actually produced a report basically saying that railways then played a prominent part in spreading that, it was not COVID then, but spreading that disease at that time. Anyway, so that is the idea, but the question that we wanted to ask here was, so I have a network of cities, we have large number of cities, towns, villages in India, and you label it like this x1, x2 up to xn, and if the infection, you declare some place as the outbreak location, meaning that where it was first located. Maybe the COVID, if I remember right, either started from some port of entry in Kerala or Bombay or something like that. So you decide your place, okay, and then the question is, can a hazard value be assigned to all other cities reflecting their risk of catching the infection. Okay. So, let us say if it was Bombay where the first report of an infection came out, what is the hazard risk, let us say, to Chennai of getting that infection. So, this is a question not about predicting how many people will get infected, it is a question about predicting how long after that first report of infection does some other place get the infection. Okay, so this is, so for those of you who already know about this SIR model, this blue line actually shows you the SIR model, okay, the standard SIR model, susceptible, infected, recovered model. To that we added this part, which actually takes into account the mobility of people from one city to another. So, this M and N here indexes the cities, okay. So, there are, let us say, M of those cities. So, quantities like F here tells you what is the probability that some person goes from city M to city N, and this is the population of city M and so on. So all the mobility information is here, and this is about how it's about the natural spread of natural infection, how it goes through its own process without the mobility. So this is what we call the augmented model, augmented SIR model. You add SIR model to the mobility information. So now it's put on a network, because we actually wanted to work with real data from India. So all the SIR model is a model, nothing much that I need to do, but for rest of the things like population of each city, we took from census data. All the mobility data we actually took from various sources. It was a huge exercise in trying to scrape data of the internet, of railroad transport networks, how many people they carry and so on. It was a massive exercise in putting together various data, and all that actually goes into all that goes into this model. And finally, we calculate what is called the effective distance and time of arrival. I will tell you what it is. So this is how what we actually did. So we considered 446 cities and towns in India with more than 1 lakh population. So according to 2011 census, all the data of train, road and air traffic was considered, and all the flight schedules were taken into account. Only things that were discarded were the local trains in, say, places like Chennai, Bombay and so on. Okay. So this actually gives you a snapshot of you can say how India travels in a sense. So most of the travel even today is by trains, as you can see that for instance the passengers per day, what we estimated was like 10 power 6 compared to any other mode of transport.
These passengers per day is during that period of time.
No, these are all averaged ones. During that time, I think anyway most of it was close to zero. And so as a network problem, so the number of nodes is 446. That's the number of cities more than 1 lakh, after subtracting close by cities like things like Hyderabad, Secunderabad and so on. And number of edges is 46,448.
What is the route symmetry index?
Route symmetry index is like suppose you go from A to B, you will always assume that if there is a mode of transport from A to B, there will also be a mode of transport from B to A. But there are many cases where you have one mode of transport from A to B, but the return mode has several different ways of coming back. There are such places in India, many such actually. So this actually talks of airway generally has that, if there is a, but in train and road that's not the case. Yeah. Okay, so this is one central result. So instead of considering, suppose what is plotted here is the geographical distance between these 445 nodes as a function of time of arrival of infection. So the time of arrival you will calculate by running that model, that augmented SIR model, and you see that there is no correlation at all between, you declare some place as your the outbreak location and then calculate the time of arrival for all other cities, and then with respect to that place calculate the geographical distance. Let us say you declared Bombay as the outbreak location, then every other city you calculate the distance from there and plot that geographical distance versus this time of arrival. You see that there is no particular relation. On the other hand, if you plot this effective distance, which takes into account the mobility of people, which takes into account how many people go from let us say city A to Bombay, city B to Bombay and so on, and then you see a nice pattern here for every such place.
What exactly is the time of arrival?
Time of arrival is how many days after the infection was located for the first time in one city, how many days later it came to the city.
Can you explain D, E and F?
So D effective, okay, I don't have a slide for it. Basically, it takes into account all the, not just the geographical distance, it's the flux of people between the two. So in fact, if let's say that there are two nearby cities, and if there is no flux between them, even if the geographical distance is small, they won't have a, their time of arrival will be large. So what matters is actually the people going, yeah. So in fact, that is illustrated by this. So let's say that Patna is for whatever reason is the outbreak location. So our hazard map gives these are the places, and this is the time of arrival in days. Okay. So it tells you the top 10 cities and their time of arrival in days. And so if Mumbai is the outbreak location, so you can see this is the time of arrival. So you can see that these are to be expected. Thane and Pune are very closely related to Mumbai, and Delhi is one of the places, it's a trunk route between Mumbai and Delhi, and so on. So one thing that you can notice is Tirupati and Bangalore are very close, I mean in terms of geographical distance, but Mumbai and Bangalore are further apart, but still it takes only 2.3 days to reach Bangalore from Mumbai and 5 days to reach from Tirupati to, it's simply a function of how many people travel. And there is actually a website that we created where you can actually play around with the outbreak location. You can choose any of this on the map as outbreak location, and it will immediately give you the next top 10 hazard map values. Okay, it sort of reasonably compared with the reality. There was a second COVID wave, and at that time we compared with the real data. So what we of the 12 cities that we declared as most hazardous based on the outbreak for the second wave, 9 of those actually did have that. Okay, so that's basically the end of my talk. So the transport and extreme events are very interesting. You can model interesting phenomena like this, but also get very useful templates for what to expect when you are talking of extreme events. And these are some of our papers, and many of them are my students or postdocs, some of whom have left IISER Pune now. So maybe I'll just show you one. I had kept that this one open. So this is that hazard map website that I said. For example, you can choose from this list any city that you want and mark it as outbreak location. Let's say if I put Chennai. So unfortunately, I think the map is missing in this. Somehow I have to fix it. It was working earlier. The India map would come nicely, but somehow it is missing. So you can see that this is the outbreak location, but the size of these circles will tell you the hazard for the other cities. So for instance, this is Bangalore, and probably Trichy or Madurai, Delhi, Bombay, and so on. The larger the circle, larger the hazard.
Is it specifically for COVID or any outbreak?
Actually, it doesn't depend on what your disease is, because it's mostly dependent on the mobility of people. See, the number of days will depend on this one. The days that time of arrival will depend on the severity of this one. Whether it is COVID or something else will matter there. But when you rank it, it doesn't matter. It will still be the same ranking. Yeah.
Like, as in like R0 is different.
That is right. Correct. But that will still be right. So that will show up in your this time of arrival. Right. Yeah, the number of yeah. So these, if your R0 is larger, then the time of arrival will be smaller. But the rank itself, relative ranks will remain the same.
But for example, if it's a more fatal disease, then it will spread to other transmitted farther because the person with a COVID disease is not able to transmit.
Yeah, so what matters is spreading, not the person who is about to die is traveling out.
No, like, so in that case, it won't travel from Mumbai to Delhi also, and from Mumbai to Mumbai.
Yeah. I didn't get your question clearly. Yeah.
So if it's a like we fatal disease, then it won't travel from far. Like you are giving.
Yeah. Okay, I agree. Okay, so I get what you're saying, but still the framework is the same. In that case, the time of arrival will be very large. Each of these time of arrival will be larger, but still this rank will still be the same. The hazard rank, like the first city to get that will still be this, but it may get after 15 days rather than after 2 days.
But so, what is the SIR model based on?
What is SAR model based on? Okay, I don't know, maybe Sithavra should answer this question, but I think it is someone's insight, like
I mean, it's basically a compartmental model
Yeah.
that divides the entire population into susceptible, infected, and recovered.
yeah,
And you see that,
you can go
susceptible
from one
and
to the other.
infected.
Yeah,
When they come together, then with some rate beta, they both become infected, and then the infected recovers with some rate gamma. So it's a mean field model in the sense that you assume that everybody is equally likely to meet everybody else. So there's no network structure there. But then you can now
Put it on.
put in a network where now you say that instead of looking at it as an entire subpopulation, you are saying that this individual is susceptible. So it has some probability that if it meets with any of the infected neighbors, then with that probability it will become infected. So if there's multiple infected neighbors, then each of these encounters would, with some probability, make it infected.
that's one cute way of modeling a very complex situation. I think modeling is about all that.
So